Third Zephyr Tech Talk. It's hard to start right on time, especially with the 30 seconds countdown. Welcome everyone, wherever you are joining us from. Oh, that was a long sentence. Whether it's YouTube or LinkedIn, I think there's already lots of people on both, basically. Hopefully the YouTube comments and YouTube chat works. A good way to try that, because I'm having doubts for some reason. A good way to try just that is if you are joining us from YouTube today, just say hi. And I see already some comments from folks. Let's put them on screen. I will start. Maybe I'm Benjamin. I'm your host today, and I'm joining from France, as you can maybe tell from the accent. Super excited to be here for a third Zephyr Tech Talk. Hopefully we will once again have people from all over the world. It turns out that you might be watching the recording of the video. That's fine too. If that's the case, it means that you're probably already subscribed to either our LinkedIn or our YouTube channel. If not, do it just now. It's the best way to be reminded in the future of new episodes. We try to do those every couple of weeks. It's a good way also to get reminded about the upcoming Zephyr 3.5 release in just about a week. Zephyr 3.5 will be out. Hopefully there will be a nice video demoing some of the cool new features. And yeah, so today we're going to talk about all things Renode. You may or may not be familiar with Renode. I've been playing with Renode myself. Many people in the Zephyr community, I believe, have been using Renode in some various occasions. And today we're bringing Peter from Antmicro to join us and talk about Renode. Hi, Peter. How's it going?
Hello. Thanks for having me, Benjamin. I'm very happy to be here.
Yeah,
and I think that it's worth noting that Benjamin himself is also a contributor to Renode.
Yeah, well, yeah, I was thinking just that. I don't quite remember how long ago it was, but maybe first things first. We have those this sort of tradition of people saying hello from all around the world. Actually, people today, you're not sharing about where you're joining us from. Last time I was super excited to see people from Mongolia and Australia and wherever else. So as I said, hi from France. Peter, you're joining us from where?
I'm joining you from Poznań, Poland.
Okay, cool. So yeah, lots of people in Europe, actually, in the Zephyr community. So yeah, why don't you tell us maybe more about yourself first, and then we will dive into what Renode is and what it can do for helping people that have needs maybe around simplifying or boosting their continuous integration, especially when it comes to Zephyr. So yeah,
Sure.
How about yourself first?
So yeah, I'm Peter. I'm an engineering manager at Antmicro. I'm with the company for 13 or 14 years already, so it's been quite a while. And I'm leading the Renode project, which is, of course, I will tell you all about it in just a second. But yeah, I'm very, very hyped being here, and we're working with Zephyr a lot, and it's a great community, and it's always fun to see how it expands and it grows, and it gets better and better every day.
I don't disagree. Okay, so should I bring up your slides and maybe we can dive into the actual presentation? People are already obviously super active in the chat, but as a reminder to everyone, we try to make those sessions super interactive. So just drop your questions as they come, and we will line them up, try to ask them whenever is best. And if some questions don't get an answer at the end, it's fine. Like there's always going to be the chat and the comment section on YouTube, and I'm sure Peter will also be sharing contact information. So with that, here are your slides, and yeah, please take it away.
All right, thank you very much. Yeah, my contact information is already on, my email is already on screen, so feel free to reach out. So the topic of today's presentation is embedded CI on steroids with Zephyr and Renode, and I will have only a very few slides, and then I will go straight to well, to the terminal and to the real deal. First of all, what's the premise of the presentation? When working with Zephyr and with embedded software, what we want to deliver is good product. It's a stable and reliable product that works the way we intended it to work for a very long time and well without hiccups. To do that, we of course need obviously a lot of testing. To really ensure that we are achieving our goals, we need to test often. So every change should be tested as well as possible. Testing should not be difficult, because if it's difficult, then people stop testing. If you need to set up 15 boards, connect them over Bluetooth, and verify that well, there's not too much interference from different sources, then it gets really difficult. You need to be able to test for regressions. So defining new test cases should not be very difficult, and you should be able to define really complex workflows. So let's say you want to verify certain environmental conditions and certain communication patterns, etc., etc. That should be all doable with the good scalable test setup. You want to test at scale, so you want to test not only well, one compilation of your binary on a single target, but maybe you have multiple revisions of your hardware. Maybe you have different, slightly different software versions as well that you want to test. Then you really need to test all of them as often as you can. And well, the worst thing you can get from running your test is the information that the test failed. And that's it. So what you really want to get out from your test is some information, some knowledge that will help you fix your software or hardware, and will move forward, get better, and actually benefit from running these tests. So what we as Antmicro are doing in the context of Zephyr and in this setup, we are an open source company, and we do a lot of open source work, both in software, hardware, FPGA, and of course simulation areas. We are a proud member of the Zephyr project. We are maintaining RISC-V architecture in Zephyr, but we also bring support for new platforms. For example, recently you could have seen us contributing a lot of Silicon Labs platforms or Ambiq. We also work on adding new specific features, and of course we focus a lot on testability and integrating with Renode. So yeah, Renode has been mentioned already quite a few times, so maybe let me give you just a very brief overview of what Renode is. Renode is our open source simulation framework that allows you to run different software. So Zephyr is one option, but we are software agnostic. You can run other software targets as well. The idea about Renode, which I will be covering a lot today, is that when we create a simulation of a platform, we treat this platform as a set of building blocks connected together. And we can leverage this fact that there is a lot of reuse, a lot of similarities between hardware, and to improve our coverage and support for various platforms. Renode supports multiple architectures and also supports running multiple nodes at the same time in a single simulation, so you can not only test your single board solutions, but also test some communication patterns, etc. We provide determinism of execution, which is important because the last thing you want is a test that fails sometimes, and you cannot really figure out why. It's very easy to integrate Renode with different tools, and I will show you how we did that with tools around Zephyr, and it provides you tons of different debugging features that I will cover very briefly today as well. Renode has been used in tons of different contexts, from IoT development to big Cortex-A and RISC-V beefy Linux-powered systems. And you can do all of it with Renode, but our main focus is always on testability and continuous integration and automation of people's workflows. We support tons of different platforms. This is by far not a complete list. I will show you how our coverage looks like later on. But yeah, we have a very broad range of platforms currently supported. I will not focus on slides. As I mentioned, we'll jump straight to the console. If you would like to have more information, there are some links. The presentation will be shared with you later, so you will find these links as well. There is a link to our website. About Renode.io is our public slide deck. Then on GitHub, you will find the resources, of course, and the documentation. But the link for today is the Renode Zephyr Tech Talk on Antmicro's GitHub. If you scan the QR code, you will see the same link. And hopefully, everything is fine with the repo, and we can jump straight to it. So let me, start Renode. All right. Okay. Actually, maybe let me start open it on GitHub first. This is our companion repo. What you will find here is a README that will tell you about the contents of the repository. It will give you information about how to obtain Renode with links to proper information sources and some additional links to different tools and features that we will be covering today. So feel free to fetch it from GitHub. There are three scenarios that I will like to cover today. First is Renode basics, because I would like to for you all to catch up on what are the basic ideas of how Renode operates. I will tell you about automation of Renode-based workflows and the integration with Zephyr and Twister as the last point. Okay, so I have this repository cloned here. So you see the same things as I showed on GitHub. Let me jump straight to the first chapter, which is Renode basics. In this directory, I have three relevant files and a README. One file is Zephyr, built for the shell module application. This is an ELF. The Renode platform REPL file and Renode script RESC. Before I show you what's inside, let me start one of the samples. The sample is based on an RF52 Adafruit feather target in Zephyr. Just give me a second. Okay. So what you see now is, Renode. You see two windows. The rightmost one, this one is for the UART output, and the left one is for the what we call it, the monitor. This is the CLI for Renode, and that you can interact with to provide commands. And to start the simulation, I need to enter the start command or just S. And yeah, this is the Zephyr sample. I can use the tab to see some tab completion that's supported in Zephyr, etc. Demo board will give me the name of the board. I will not tell you how to interact with Renode in very much detail. I am only focusing on certain aspects here. But the point is, this is the typical view you see when running Renode. And this window-based mode is only one of the options that you can use to talk to Renode. So let me talk a little bit about the files that we have here. Also, very briefly, just to give you an idea of how we create a simulation. Let me start with the RESC script. It's a very short file. It's similar to all Zephyr targets. It contains a list of commands that we can type in interactively in our Renode monitor, or just load them from a script like we did just now. So what we do here, we create a machine, a new entity in our simulation. We load the platform description. This is the REPL file that I mentioned before. I will show it in a second. We open a window for a specific URL that will contain our output. We load the ELF file, and then we just move forward with the simulation. So this is conceptually very simple. Hopefully, there might be some details that are more complex in the syntax, but the idea is simple. Create a machine, load the description of the platform, load the binary that we want to test, and, for example, open a window for a UART. The REPL file on the other hand, is a description of the platform itself. So you will see things like CPU, like interrupt controller, like the GPIO controller, memory block, RNG, connected with some interrupts available on some address on the bus. This all should look very familiar, especially to Zephyr users, as Zephyr is strongly based on device tree. We generally tend to cover the very similar information.
So I guess I'm going to ask before maybe you answer that question, but is this or could this be actually automatically generated from device tree
I will
information?
get there.
There you go.
Yes. That's definitely a significant part of my presentation today. But yes, the spoiler alert, yes, this can be generated.
Awesome.
All right. So yeah, this is a basic setup. Everything we need to run a simulation is here. Renode installed system-wide, a script, a platform description, and some binary payload. So hopefully that gives you a basic understanding. But we are not talking today about this interactive use case too much. We will talk about automation. And in the second part of my repository, I have, let me clean up from the previous run. Thank goodness I made this script. So here we have 4 different use cases I want to show you. Oh, let's say 3.5. First of all, I told you that the CLI, the pop-up CLI with a window and logo is not the only way to interact with Renode. And when we created Renode, we wanted to be easy to adjust to your workflow, to your typical workflow that you might have with your other tools. Well, the obvious idea is batch processing. When you have some commands that you run from a script, and then you, for example, wait for some results, and you do it, for example, from a bash script. So let me open the first script, run renode.sh. This is the very trivial example. It contains 2 cases that are basically the same. Renode can be installed in 2 ways. It can either be installed, well, from a package or from a portable package that you just download, unpack, and add to your path, or it can be installed via a Python package called Renode Run, which is a little bit easier, but, well, I believe some people prefer one and some people prefer the other. So here the script covers two cases. I will focus on the first one. It starts Renode with an option to disable the UI and opening a port on a specific port number. Let me do it. Oh, it tells me that, yeah, connect using telnet localhost 5555. I will do that right now. Telnet localhost 5555, and voila, this is the same monitor. And of course, it doesn't look very surprising. What I can do is, for example, I can run a script from one of the Silicon Labs boards, SLTB004A. Since I told Renode to disable the UI, I will not get the additional output from additional window with the UI. But if I start it, you can see the output being printed in the log. This is one option. You can also redirect your log, your output to a PTY object in your system, or also to a socket, just like we did with this monitor via telnet. But this simple basic batch mode already allows us to do some automation. So, for example, you can write an expect script that connects to a socket and waits for something to appear, then sends some output, then waits for something else, etc., etc. Spoiler alert, this is one of the options we use to integrate with Twister. I will cover that in a second. So let me close Renode right now. The second option I wanted to show is a little bit more involved. It's called It's using a library that we implemented called PyRenode. You might guess that it involves Python. So here we have a Python script. It's a very trivial script that does several things. First, we declare which UART will be interesting for us. We connect to Renode using this a function from this library. We initialize some additional functions, and then we get access to what we call keywords. I will tell you a little bit more about what these keywords are just in a second. But the idea is that you get this method and you don't have to parse output from the UART manually and to write a complex bash script waiting for some event to occur. Here we provide a set of helper functions that allow you to, for example, execute command in the monitor, start the simulation, wait for something to appear on UART, given that we observe a specific UART device, write something back, wait for something to appear on UART, etc., etc. It allows you to simplify the whole flow. You don't have to handle sockets manually. You don't have to parse input output manually. Everything is done with these convenience functions. And these keywords are keywords that we actually use in testing, which I'll show you in a moment. Just let me run the script first. So right now it's starting Renode underneath. And this long list of keywords is the actual information about what functions are provided by this integration. So you can reset the simulation, start it, execute command, wait for a pause in the simulation. Well, many different options. And all of these keywords are keywords that we use in our day-to-day testing with our main integration that we created for testing purposes, which is using the robot framework. This is the next part of this directory. You will find that we'll have two files with the robot extension. Robot is a Python-based framework, again Python, that allows you to write tests in more or less English language. It doesn't require too much technical knowledge, but we have created a specific integration to provide this functionality, so it's very easy to write specific test cases. Let me show you one. This is what a typical robot test looks like. Here we have a Leon free platform, also running Zephyr, also a shell module, because that's very easy and I don't need to go into details of what the application is doing. What are the main components of this test? Here we have some variables, which are not that important, but I guess they're fairly understandable. We have helper keywords. This will become more important when I talk about more Zephyr specific things. But here we have a keyword that allows us to simplify each test case. So we have a prepare machine keyword that declares where is the binary, loads the script, loads the terminal tester, so that we can write something back and read back from this UART. And here we have two test cases. One tells us that the Renode should boot Zephyr on this application. So we prepare a machine, we start the emulation, and we just wait for a prompt. So that's fairly trivial. And then we declare Zephyr is booted, so we have a state called boot Zephyr. And then another test should print version that relies on this previous state, but also writes something to the UART of command version and waits for some output back. You see that these commands that we have here, write line to UART, wait for line on UART, are the same that we used in the Python integration, because they're basically the same code, just exposed in a different way. What is important is that we not only have integration for UART, you can inspect network traffic, LED status, all the details of the simulation, memory contents, whatever you like. This is, of course, just the most basic example. But if you go to our Renode repo, you'll find more advanced cases as well. So let's run it. I have a Renode test application that I can run on the robot file. Just give it a second, and we will see the results of the test along with some additional files generated by robot itself. Just one more second.
Actually, I've heard about robot framework for the first time while looking into Renode myself. Like, can you tell us a bit more about like what it is, like where is it coming from, and maybe why you ended up picking it up as your framework of choice for automation?
Sure. I believe one of the main advantages of robot is, first of all, that you don't have to recompile any code to create a new test case. They're all written in a declarative way. First of all, it's super trivial to write simple stuff because you have these keywords that you can expose, and they are connected via XML RPC to Renode itself. But on the other hand, if you want to do something very complex, if you want to write Python code that does some heavy logic underneath, you can also just load a Python file as a resource to such a test and do actual heavy lifting underneath so that your test case is still fairly easy and readable. That means that it allows you to kind of decouple people who write tests from let's say low-level programmers. This is fairly easy to learn and to write new test cases. I think that this ease of use is one of the main reasons we use that. It has been quite popular in the context of I guess data science and this kind of workflows. But I also have seen it in well, various places. So this is absolutely not in any way Renode specific. We only added integration that allows it to be used with Renode quite easily. Of course, it gives you all the additional functionality, like all the system services. You can access files on your host, etc., etc., which makes it like very easy to write really fun test cases.
Nice. Quick question from Pascal before you move on. Is it possible to migrate the tests done in robot to test the actual hardware once we have it as part of the regular testing in, say,
That's
CI?
a fantastic question. Actually, yes. If you, I will get back to this question later on when I show a test that we have created for Zephyr for shell module in Zephyr itself. But you can provide alternative implementations to these keywords. So we do have Renode users who have exactly same test cases running both on in Renode and on hardware. Just with different implementations of these keywords. And of course, they have to be carefully crafted because start emulation probably doesn't make sense when you're running on hardware, but you can create abstractions and just replace these abstractions to have the same test case running on both real hardware and simulation. But I will get to these resources and replacing implementation later on. So as I ran this test, I got some files created, but all the tests passed, so they're not that interesting. I also have a failing test that is very similar. It's actually quite the same, but I only replaced the Zephyr version at the very end with some bogus number. So let me run it. And here I will be able to show two interesting features. First of all, we will get a report that will tell us that, hey, something went wrong, obviously. As soon as the timeout on that printing hits. So this is the report from Robot. You see that there is, well, we managed to connect to the UART. We typed in the version. We got this line, but we were expecting this line. And this is, of course, a console output. If you have many tests, it doesn't really scale very well. But what you can do is you can open the report, which is like a very nice HTML generated summary of all the tests that you have run with all the details of the keywords. This is a feature of Robot itself, but we use it very often, and it's super useful to analyze your failed tests. As I mentioned, one of the feature of a good test is that it gives you some knowledge about what happened and allows you to reason about your setup. So you might see that we have two new directories. Logs is not that important, but we have a snapshot directory. In the snapshot, we have a save from the whole simulation from this test that actually failed. I can run it. I will start Renode. I will load this save file. Load all 4 failing tests. I have to just reconnect my machine and open the window manually. Oh, sorry, I forgot the name of the UART. Oh, that's just UART. As you can see, you can access all the details about every peripheral at every time. And you see that, well, we have typed in the version command. This is what we got as a result. And of course, this is a fully functional simulation. So you can type in help and it is still working. So that's what you typically run on your CI, and you get these snapshots as results, and then you can analyze them on your own local PC and share with your friends and discuss them in more detail, and inspect every detail about what went wrong so that the test failed. I think that it's a really powerful feature, and we use it quite a lot. All right, so I showed you how to automate things with Renode, that you can run a batch mode, you can use Python, you can use robot tests. So let's get back to Zephyr itself. In our repo, we created, we forked the example application repository that is provided by Zephyr, simplified it a bit, and well, initialized it as a standalone out of tree Zephyr application. If you want to run it yourself, what you would do is west init -l example application and then west update. I have already done that, and it takes some time, so I will not repeat the process. This is all covered in the README, by the way, so it should be trivial to reproduce it. Again, I ran a lot of previous test cases, and I didn't clean up after myself. Shame on me. What we have here. Here we have a very small Zephyr tree with 2 applications, Hello World and Shell module. They are, of course, the same as we have in the main tree, but I copied them here for convenience. And I have 2 boards that are created specifically for this demo. And of course, they are not created from scratch. They are modified versions of what we have in Zephyr. So if I go to board, ARM, here you see STM32F7. This is one of the STM32F7 targets that is available in Zephyr. But also we have a RISC-V target, which is called Unleashed, which is the same as HiFi Unleashed with some additional configuration done by me. I changed these names just to have them distinctly selectable and different from what is available in Zephyr. If you want to have your board supported in Zephyr test system, what you have to do a certain set of steps. Let me go to ARM STM. This is the directory of this board. There are 3 steps that you have to make to enable testing with Zephyr. First is in the board CMake file. In the board CMake file, you declare that Renode is a supported emulation platform. You point to the script that covers this specific platform, and you say which UART is interesting for you. This could be probably extracted from device trees, but as this is a CMake, well, this is a different stage of compilation, so we decided to keep it as a variable. So these 3 lines are actually everything that you need to have from the CMake perspective. There is also a YAML file, STM32F7 YAML, where you declare these two lines: the simulation renode, simulation exec renode. As far as I remember, Zephyr schema requires both fields to be present. And the last point is adding the script itself. So here we have a RESC script and a REPL script. OpenOCD was here before if you want to run on hardware. But these are exactly the same as you have seen before. Getting back to the question by Benjamin, you will see that the rep file has the auto-generated header, which I will get to in a second. So let me run some tests. I do it with West Twister. I will select first the STM32F7, and I will run hello world test. In this integration, we use this batch mode that I told you about before. So we connect the Renode monitor to a port. We connect the UART to a PTY device, and we use Twister infrastructure that is already there to input and to get output from these runs. Of course, running Twister requires us also to build the simulation, to build the application. So it takes just a little while, and me sharing the screen probably doesn't help. But you can see here is that, well, one test configuration executed on platforms. I can assure you I don't have any Renode, any STM32F7 connected, but well, to be 100% convinced about it, I can add some verbosity. Let's switch to Unleashed platform and run shell module. In shell module, we use a different type of integration that I will show you also in a second. Here we use a robot test. So Zephyr and West and Twister right now support running robot tests as well. And if you go to the shell module on Zephyr upstream, you will find the test case listed there as well. Just give it a second. It needs to build this application. There are 3 tests left. And we should have the results in no time. You'll see that.
Let's take a quick question, not necessarily directly related to what you're showing right now, but Anuraj was asking, what if I want to emulate some kind of TFT display controller for my embedded GUI using LVGL? How would I go about doing this?
Let me show you. So that's actually quite similar to what you've been working on, Benjamin, right? Yes. So one sample demo that we have is on, well, actually F7 that we are covering here right now as well. So you can actually have a support for UI. Well, this is probably not looking very good when it's streaming, but we do have support for screens, LCDs, etc. Of course, you need to have a
touch controller as well, if I remember correctly, right?
That's correct, absolutely. Cool. So you can have both input and different versions of output. All right.
That was easy.
Yeah, we have a demo for that. If there is a demo, I can show it. All right. So getting back to the shell module, you could have seen that there was actually a log about Renode running, and to have a robot test run in such a test, you would modify a sample YAML file, and you would add a test specification using the robot harness. So the harness is called robot, and then you provide a path to the robot file, and the robot file is in the same directory. You will not be surprised by what you see. We run version and we wait for some output. I don't even specify the version number, of course, because this is a well, generic Zephyr test, and it will be changing as we go with different versions. One thing that I wanted to mention is that there is also a Zephyr-specific robot file, which is called common robot. When we are running Twister, it is loaded as a resource. So this is a variable that is provided by Twister. and it contains an implementation of the prepare machine keyword. So I can actually show it. It will be here. Sorry. Zephyr tests robot, common robot. It's very trivial. It loads a binary, it loads a script, it creates a terminal tester. These are the variables that we have defined in the CMake file. So yeah, it's kind of trivial to figure out how to work with this. And of course, this can be expanded to either work on hardware or have more features as well. All right, so we were able to run a sample in Zephyr with Twister using Renode integration. This is already supported by upstream Zephyr, and instructions how to enable your platforms and enable additional tests are all in README in this repo. Let me run one more test once again. Hello world. I will add some verbosity here because I wanted to get the specific command that is being, so we see Twister itself is doing a lot of work here before we start the simulation. We are building the sample. And I'm waiting for it to.
Let's take a question then.
Yeah, absolutely.
What if the test involve, or the simulation in general, involves some actual sensors? Are the sensors automatically mocked, or does one have to write a C# plugin for every single one?
So yeah, in general, you would write a model for a specific sensor. We have a system that allows you to to provide data in a very timely manner to sensors. So we can have a specific setup and pre-recorded sensor data that you provide to sensors, but you would have to have a model. If you don't want to have a model, you can also pre-record communication I2C or SPI bus and create a mock that will just feed it on each interaction. But you will have to have some kind of idea on what you want to model and how do you want to connect it. So some kind of a mock will be required.
Right.
Yeah. Let me run the command that has been started by Twister just without the UI and without starting the simulation. I mentioned that you want to get as much information about the run as possible. So I wanted to show just a few features. I have to be conscious of the time flow, so I will limit myself to just a few. Let me start with the profiler. What I'm doing right now is I enable the profile creation of a collapse stack format profile of the simulation. Let me run it. Hello world. Not surprising at all, right? But what I got in as a result is the profile file. This can be opened by a Speedscope application, and it gives you this sweet output. Thread, actual stack trace of the execution at each moment. You can of course do some analysis of where do we spend most time, where do we, which function called which function. This kind of visual analysis gives you tremendous input, a lot of knowledge about what's actually happening in your software. Of course, you can create this as logs as well, but this is not the same as actually seeing what your application is doing at any given moment in time. This is super useful, and I will get back to this feature as well in just a sec.
Just to be clear, similar, because there was a question earlier, similar to the snapshots, like it doesn't matter whether you're using robot or like raw CLI or Renode, like it's an actual Renode feature that
absolutely
does that, right?
Absolutely. So this is all let's say included in the framework itself. Let me run it one more time just to give you some, I will not cover details of what I'm running right now, but I will enable a lot of logging. So I will enable logging of accesses to peripherals, logging execution of function names in your ELF file, and yeah, so I can. Oh, I'm running STM32F7. If I were running RISC-V, I would be able to also, for example, get analysis of each opcode that is being executed in the simulation. So right now, when you run it, you can see that in the log window, you see a lot of function names from your binary, but you also see accesses to peripherals, and both this information combined gives you tremendous amount of knowledge about what's happening in your system at any given time. And this is, of course, also a Renode feature. All right. I mentioned that you are able to run, to get logs up to the level of opcodes that are being executed. Why would anyone need that from a functional simulator? I wanted to open one blog note from our blog about TBM. This is a functionality we've been working on with Google, where when you have the information about the execution from a functional simulator, it doesn't really reflect the performance of your software. But if you have knowledge about the microarchitecture that is beneath, you can get these detailed traces and expand them to actually learn a lot about the performance in a post-mortem analysis. And this approach is called trace-based modeling. There is it is also supported by Renode with a tool created by Google. So if you're interested, I recommend this blog note on our blog for further information. So I will not go back to the console. I wanted to show you. I mentioned scale. So you asked if we can auto-generate these device trees. Actually, we can. Because we can, and we created a tool called DTS-Rep, we were able to create the Zephyr dashboard. Zephyr dashboard is our website where we run each Zephyr target with more than 520, I believe, on several different Zephyr samples. And for the Hello World, we are able to get almost 300 passing test cases. Just because we have the DTS file, and we can generate rep files of it. I told you that I will not get back here, but I will actually run DTS. So DTS rep, you will provide the DTS file you built from Zephyr. This is when you build Zephyr, this is actually a flattened device tree, which contains all the information from the board, from the SoC family. This makes it easier for us to build the platform file.
Yeah, you don't need to have a full-blown Zephyr dev environment setup since everything is already in line in the.
Yeah. So yeah, in this case, this is actually from a build directory. So this is a pre-built Zephyr, right. Well, the one that I just built. But you could also do it from this let's say separated DTS files as well. And yeah, so this is the DTS file that I had as an input. It contains, well, GPIOs connected somewhere, etc., etc. And this is the platform file that was generated for this specific platform. So this allowed us to build Renode dashboard and run multiple tests. From this test, we extracted as much information as we could, which led us to creating Renodepedia, which is supposed to be this encyclopedia of hardware, this big repository of information where we also store these traces I just showed you, when you can inspect the UART output of each sample, test results, etc., etc. It's all there, and it is possible because we're not running this on hardware, because we're running it in simulation. Yeah. By the way, we also have a U-boot dashboard because U-boot also relies on device trees, so we can do a very similar thing. I mentioned Renodepedia, but last one thing I wanted to show you on our repo is the if you go to this Renode Zephyr Tech Talk, you will actually see that there is a GitHub action flow, and this is yet another way to employ automatic testing with Renode in your GitHub Actions. We have prepared an automatic action that will do exactly what you saw me doing in the console just a minute before. And declaring it is super easy. If you have your robot file created, you run these 5 lines of code in your GitHub Actions code. You say which version of Renode, which test to run, and that's virtually it. Then you can also, save some artifacts for further analysis afterwards. We also have a similar GitHub action for testing applications running in Linux for RISC-V and ARM platforms, but I guess I won't be able to cover that in much detail today. So before I say goodbye, I wanted to tell you that this is not only for running Hello World and Shell. We have been testing very interesting big scale applications that are actually running in products that you use. So for example, we've been working with Google on testing their fingerprint module that is part of the Chromos project. When we are running massive CI on GCP using GitHub Actions, there's a blog that you can read on that. And also another interesting case for wearables case where there was a customer that actually had a setup where they had a lot of data that was very constrained in terms of timing. You had to analyze this data coming from the sensors in very precise moments of time. And to verify that their application is working correctly, they wanted to test 24 hours of execution, constant execution and crunching this data. Of course, you could do that on hardware, but that would take, 24 hours, and you would have to mock the sensor input somehow physically. With Renode, we were able to get under 2 hours of runtime, which I believe is quite a nice achievement. It gives you reproducibility. You can run it in CI. You don't have to have complex sensor mocking, etc., etc. So yeah, this is definitely not only for small pre-built for samples. This is for real use cases, and I hope that you will be able to use it in your development and scenarios as well. That's it from me. I took the great part of the hour, but I would be, of course, happy to take your questions if you have any.
Perfect. Awesome. Yeah, well, there are still some questions. I think your colleague, Michael, took most of the questions by text in the respective chats on LinkedIn and YouTube. But I guess maybe as a way to wrap things up, what's going to be the future of Renode? Like, what are some of the things that you can talk about, at least in the roadmap? Someone, Anuraj, was asking, how about support, for example, for Extensa and ESP32 in particular? There were some questions also with regards to, and this might be actually some features that are already somewhat possible, but what about connecting real sensors to the simulation? Like if I have a Bluetooth controller, or if I have a way to physically connect to an SPI or an I2C bus, like can I physically interact with real sensors? Things like that. Like any, tell us about the future.
Very good questions, all of them. So regarding the future, we have quite a lot of development recently in the areas of Cortex-R and new Cortex-A's. So Cortex-A's are mostly for Linux grade systems, but Cortex-R is definitely in the scope of Zephyr users as well. So stay tuned. There will be definitely more. We are working a lot on the sensor support and this timed input of sensor data. It's been a very, very nice development. I forgot to mention that we are working on a new Python interface that would allow you to hopefully fully replace our bespoke CLI with just Python object-based solution. This is also in the works. I should also mention Visual System Designer that allows you to somewhat graphically design a system, and then, for example, the idea is, I hope I will be able to show it right now. So this is Visual System Designer, and if you enter a specific board, you can try to modify it. Unfortunately, and then we would like it to be able to also generate a Zephyr configuration for the board that you create, Renode configuration for the simulation purposes, and do a lot of custom prototyping in this kind of system. So there's a lot of development going on, and a lot of them are driven by our partners and our customers who want us to add specific features, and then we focus on them, obviously. But of course, there's a lot of internal R&D going on. You also asked a question. The last one was about the connecting through the sensors. That's also interesting. I mentioned that we can connect, for example, UART, but you can also connect USB to your host. You can also connect Ethernet to your host. We've been recently playing with HCI Bluetooth connections. So these kind of scenarios are actually what we want to enable with Renode. Connecting to real life is definitely an option. We have options to connect to even SoCs that are partially on a PGA platform and partially simulated in Renode as one, and treat them as one SoC. So I definitely recommend you to go to our blog and scan through a lot of articles that we have there. Hopefully they will be an inspiration to you.
Nice. Yeah, as a reminder, I'm putting the link again to the GitHub repo. Just to be clear, everything, all the demos and everything that you've shown today that was using Renode or Robot Framework and things like that, everything is open source, right?
Absolutely. Yes, there's no secret sauce underneath. Everything is publicly available, and this repo contains all the details. Renode is fully open source. There are no hidden features anywhere. It's also permissively licensed, and we just want people to use it to find new ideas of benefiting from it, and of course then contributing back. Or we as Antmicro are always happy to support different use cases, and we invite people to reach out to us. And if you have a difficult test case that you would like to cover, or a specific scenario you'd like to have supported, or a specific platform that we don't yet support, then of course reach out, and we should be able to help you.
Awesome. So I think we're reaching the top of the hour, and we've reached not the Godwin point, fortunately, but the ChatGPT point in the chat. People are starting to talk about how ChatGPT could potentially help generate test scenarios and whatnot. So I think it's time to wrap things up. So yeah, thank you very much for your time and the presentation. There might be some questions that we didn't get to. So people, please just ask again, if you don't mind, in the YouTube chat or on LinkedIn. We will make sure that those get answered. You can also reach out to Peter. He shared the contact info earlier. Hopefully we will be back in 2 weeks' time. Actually, that's an ask for anyone watching the video today. Our speaker initially scheduled had to cancel, so it might be that there won't be a session in 2 weeks' time, but I would love for one to be there. So if you have a topic that you're passionate about, and if you feel like talking about it on the show, as you saw today, it's mostly demos, hardly any slides. So if that's a topic you're passionate about, it might be that you can actually jump on the opportunity. Feel free to reach out to me, benjamin@zephyrproject.org. And with that, see you in a while, hopefully in 2 weeks' time. Bye, everyone. Bye, Peter. Thanks again.
Thank you very much. Bye.